Hi, everyone. So I'm Kelly. I'm a machine learning engineer from Canva. Who here has heard of Canva before? Oh, nice. Who here has actually used Canva before? OK, so a lot of people, actually. So for the few that don't know Canva, we are a design software company, and our mission is to empower the world to design. We do this by providing a platform that effectively builds and scales creativity. We currently have over 190 million monthly active users. This is across 190 countries and in 100 languages. And to date, we have over 25 billion designs created on Canva. That's over 200 designs created per second. And today, we'll be telling you the story of how we scaled AI at Canva and reduced our training time by 25 times. So in the beginning of our journey, we had around 80 machine learning engineers. So these are actually machine learning engineers that are embedded into platform teams that build products that you see on the Canva interface today. Our MLEs would use the platform to prototype, train, and deploy their models. We had about 80 productionized models and do roughly 1,200 training runs every month. So this can include like experiment or production cron jobs. A quick overview of our ML platform architecture. This is the typical process you will follow when building a model that is intended to be productionized at Canva. So you start with this proto file. I'm not sure if any of you has heard of that before. It's like an API contract. You would define the schemas of your model server's inputs and outputs. And then next is your training and serving logic that is written in Python. And then we would use Bazel to package everything up. You would iterate these steps as a local dev loop. And then once you're satisfied with your local training, you can scale your model up into the cluster dev loop. So this would involve building an image on CI, and then compiling a training manifest, and then you finally run that workflow on Argo, which is in Kubernetes. At the end of the training cluster dev loop, you'll have these model artifacts that can be layered into a production-ready container and deployed as an endpoint to serve whatever feature that we have on the front end. So this architecture has served us pretty well in the past, but it was quickly evident that it will not get us to where we want to be, especially with the generative AI tsunami. We needed to be able to do ML fast and be able to take ML far. It was crucial that we provide our machine learning engineers with a flexible and interactive prototyping environment, as well as a paid role for optimized training routines. Some of the bottlenecks that was hindering us from achieving ML fast and far include compute. So firstly, training was limited to a single node. While there were ways for us to achieve single node multi-GPU training, it was a bit difficult to set up, and not many machine learning engineers ended up using it. We also lacked a proper IDE support. If you wanted to prototype in a bigger compute instance, your only option at the point in time was a Jupyter notebook in our Kubernetes cluster. Lastly, we had divergences in tech stack. We had another ML platform team in Europe that was working on a completely different stack. So this lack of a unified model training and prototyping experience made it really hard for us to maintain. So we revalidated various vendors and decided to go with Ray and Anyscale. What we really liked about Ray was that it was open source and had a strong adoption. And combined with Anyscale, it meant that we had commercial support and the ability to do multi-cloud all under one account. So began the process of integration. One of the early challenges we ran into was accessing data. Our AWS accounts were split into a control plane and a data plane. The data plane is where resources such as secrets, buckets, queues are located. Teams would create roles in this account that would grant access to their team resources. And the control plane was where the compute happens. So stuff like our EKS cluster, where any EC2 instances would be located in this account. This worked well with EKS because it uses IAM roles for service accounts. So we were able to map our Kubernetes service account to the corresponding trainer role. And then the training workflows on each pod would be able to assume the trainer role automatically and access the team's data. So when we started setting up Anyscale cloud resources, we aimed for something similar. We created a single organization and then created clouds for each team. Each team would then spin up their own EC2 instances, and then these EC2 instances would have their own instance profiles, which then link to a specific trainer role, and then you can get data that way. And we thought that would be happy days. We quickly found out that EC2 instances do not, the instance profiles itself do not support cross-account, so some additional massaging was needed. We had to create role assumption policies to allow the EC2 IAM roles to be able to assume the corresponding model trainer role. Then at the start of each training workflow, we had to write an AWS config file to a storage location that all worker nodes have access to. This allowed the application to assume the model trainer role at runtime. So that solved our data accessing issues. And then we ran into another challenge. So this one had to do with the base images actually used for launching clusters. The Anyscale base image comes with a lot of pre-installed packages as well as Conda. So these were great for launching a workspace where you just want to do some quick and dirty prototyping or a sandbox. But it wasn't something that we wanted to use for our production workloads. For production, we stressed on being able to do reproducible and hermetic builds. And this was achieved by using Nix and Bazel and a single Python monorepo dependency. So we worked for a while with the Anyscale team to obtain this base image that only had minimal requirements for launching a Ray cluster and to pass the required health checks. And then we used this minimal image as the base image and then layered in our in-house Nix package layer. And then lastly, in each model trainer's Bazel file, the PyPy dependencies are added in, as well as the trainer code here. And then the final output you get is a model trainer image that can be used in the cluster dev loop and then used as a productionized cron job. So with the integration challenges resolved, we pushed forward with our migration. During the early adoption phase, we scoped out all the required changes for possible use cases, such as single node and multi-node training, tabular models, and how to handle models that need to train in both global and China AWS partitions. So we then started to onboard teams to Anyscale workspaces, as well as moving the training workflows to Anyscale jobs. Overall, it took us from general adoption to fully migrated around 6 months. We also now have close to 30 clouds on Anyscale, and we run around 2,000 training jobs every month. And we deprecated our self-hosted Jupyter Hub solution. Our users now use the Anyscale workspaces for out-of-the-box VS Code, IDE, and notebook support. Some of our key results include scaling up a fine-tuning job on the XLM Roberta. So this training job used to run on a single A100 GPU for close to 3 days. We scaled up to 16 A100 GPUs, so 2 P4DE 24X large nodes, and it now runs around 3 hours. And not only were we able to speed up model training, we also saw an uptick in prototyping and experiment turnaround speeds. For example, we were able to fine-tune 50 LLMs in less than 10 days using Anyscale as part of our exploitation task to replace a model that we currently use for intent classification. And now I will pass it on to Amar, who will tell you more on what else we did.
Thanks, Kelly, for the amazing tour so far, and hello, everyone. My name is Amar, and I'm a machine learning engineer here at Canva. And so far, Kelly has talked about what it meant for us to switch our training infrastructure to Ray and Anyscale. And now that we had it in place, there was one thing that we always wanted to try, but in our previous setup, we thought it was too much effort. And that was to push the boundaries even further with out-of-band validation. So first up, what is out-of-band validation? And to really figure it out, let's just go back to the basics and look at a standard training process. So usually you have like a single machine, or these days like people run on clusters, so you have a homogeneous cluster that performs both training and validation. And so using this compute, you run the training step, and then after each step, you stop the training, you switch your model to inference mode, and then you perform a validation step. But the fact is that the training step doesn't depend on the validation step. And this is something that we could use. Instead, the training process could look like this. So we run the training step on our existing compute. Let's just call it compute 1 here. It can be a single machine, or it can be a cluster of homogeneous machines. And after that, we run a validation step. But that step runs on a different set of machines. And let's just call that compute 2. It can be same as compute 1, or it can be a set of some cheaper machines. And now, after each training step, we use the other compute to run validation in parallel. And the nice thing here is training doesn't have to wait, so we can go to the next training step already. And once we are done with our validation step, we report back the validation results to the main training run. And then we repeat this process. And this we call out-of-band validation, and it's a setup where two machines or a heterogeneous cluster can perform training and validation separately in parallel. And that was the basic idea. But how does this work with Ray and Anyscale, and how is it exposed to our MLEs? So to answer the latter question, we're first going to take a look at how this is used by our users, and then we're going to go into the details. So usually with Ray, if you use Ray train, you have your train func, and here it's my train func, and we modify its config that we pass in to also pass the validation dataset in. And it's pretty basic. We use the PyTorch Lightning framework, and we have some callbacks that we use. And those are then used in the PyTorch Lightning trainer. And yeah, to this list of callbacks, we add our out-of-band validation callback. And additionally, the users need to be aware of which mode their training function is to check if it's like running on the main training worker or running on this out-of-band validation loop. And depending on that, they will like trigger a different method on the trainer. And that's it. Usually these few modifications are enough for our machine learning engineers to start using out-of-band validation. Now that we've answered the question on how this is used, we can go a bit under the hood and see how does this actually utilize Ray and Anyscale. So first up, we saw this add out-of-band validation callback function, and basically it has two possible states. So the first state is if it's running in the main training worker, and in this state, a main loop out-of-band callback is added, and this callback launches the validation runs, tells the validation runs where to find the checkpoints, and also eventually picks up their results. And the other state is when you're running in the validation-only runs, and there we have a validation loop out-of-band callback, which operates independently on validation workers. It focuses solely on executing the validation process, but it also has to download the model checkpoint, set everything up, capture the validation metrics, and then once validation is performed, report these metrics back to the main trainer. And yeah, now let's take a bit deeper look into how these callbacks work. So one interesting event is the end of training epoch, and we should like see what happens there. So over in the main training loop, we have, as you remember, the main loop out-of-band callback running, and it's going to get triggered on the train epoch end. And we assume the checkpoint was saved by the user using RayTrain report, and we're able to pick up this checkpoint location and then start a new RayTrain torch trainer. And we do that from the global range 0. And this new trainer will only perform a single validation loop. Over on this side, the validation loop out-of-band callback will first download the checkpoint on all local range 0s, and then after which all the ranks will load the model weights in. And then the validation can begin. And as we mentioned, the training doesn't have to wait. We also start training. And another interesting event is the end of the next training epoch. So coming back from the other side, we had the validation loop running, and it was capturing the validation metrics, and now it's time to report them back. So on global range 0, we use RayTrain report to report the captured validation metrics. The training loop then picks them up and passes them on to the weights and biases logger. And once this all is done, the process repeats again, and the next out-of-band validation run is started. And finally, how this looks like in the code. So we have the main loop out-of-band callback. It's a standard PyTorch Lightning callback. We had a setup method, which is executed only once during the training start. And there we want to disable the validation runs in the trainer. So that's something that we do for our users so they don't have to think about this. And then in the on-train epoch end hook, we use this report and launch new, which coordinates the transition between validation runs. So it reports the old validation runs, and after that launches a new one. And how does it do this? So the main magic in the main loop out-of-band callback is this function, remote torch validation. It's basically a Ray remote task that runs in parallel to the training, and it actually just triggers another torch trainer. And you may be wondering, like, how do we know whether we're in validation or in the main training loop? So we use this metadata field, which is only set for the validation loops. So in the main training loop, this is not going to be set, and that's how we're able to discern in which state we are in. And finally, for all this to work, one last thing that we needed to configure was to set the Ray remote task to run outside the existing placement group. So we looked at how this all works, but why would you switch to out-of-band validation? So first up, it saves time, which means a faster dev loop for our users. And the way it saves time, as you saw, is in the original setup, you run training and validation one after each other, while in the out-of-band validation, you're able to parallelize some of that tasks. And that's the time you save. And we can also look at some numbers. So we ran some experiments on different model sizes. We looked at train data to dataset ratio of 80%, and we ran the training, example training for 100 epochs. And overall, we saw an average of 7.4% training time reduction. And with smaller train data to dataset ratios, this can go up to 18%. And furthermore, this also saves money. So why would it save money? Because we're now using more compute. So without out-of-band validation, we would use a single type of compute for running both tasks. And in the other setup, we would use even more compute. But the nice thing is, in the first setup, we would use a single instance type. In the second setup, we were able to use a cheaper instance type for inference. And so we would still save money even while compute one would wait for validation. And that was like the main reason of saving money. And furthermore, we can scale up compute to only when we need it. And let's look at some numbers here as well. So as we said, the cost doesn't increase. In fact, it's cheaper. So in our experiments with the same setup as before, we observed 3% cost reduction on average. And similarly, with going to a smaller trained dataset ratio, this can go up to 8% in cost reductions. There are, of course, some gotchas. So when should you not use the out-of-band validation? First up is if your validation dataset is too small. So as you saw in the experiments, if we would decrease the size of the training dataset, the validation step would take longer, and then we would get time savings and both cost savings. But if the validation dataset is too small, eventually the overheads take up all your time, and that's when you shouldn't use it. Also, you shouldn't use it if validation now takes longer than the training, because this is going to block the main training loop. And finally, if the validation instances, which are usually cheaper, cannot fit the full model. And to wrap up, so we used Ray and Anyscale to enable out-of-band validation on heterogeneous clusters. Why did we use it? Because it saved time, which meant a faster dev loop for our users, and the cost didn't increase. In fact, it was cheaper. And finally, looking back at today's talk by Kelly and I, here are some key takeaways. So first up, speedups does not equal lower cost. It can be tempting to scale your training to a lot of distributed nodes because Ray makes it easy to do so. And let's be real, it's pretty cool to see a training job like take up 40+ nodes. However, faster is not always cheaper. Oftentimes you need to try out different instance types and worker numbers to find out the optimal balance. Ray makes it easy to implement out-of-band validation. It definitely was worth a try and may give you further cost savings. And lastly, a huge shout out to the Anyscale team for their continued support on all our training and scaling issues. And with that, yeah, the presentation is, we're up in the question section. Okay, so are there any questions or? Yeah.
So what are the typical models at Canva?
So the question was, what kind of typical models do we use at Canva? Do you want to? So it ranges really from, depending on the task, like starting from search or recommendation systems, then all the way up to the Gen AI features that we've recently deployed, and like photo editing features. So yeah, it's a pretty wide variety of models.
Just trying to understand what out of these categories of models that you mentioned, for which ones would you suggest, are you guys using and you suggest to use the out-of-band setup, and for which you suggest not to use the out-of-band setup?
So one recent example was one team that was training a model and was really performing lots of experiments, and for them it was really valuable to be able to iterate the model faster, like go through the training loops fast, but also be able to perform lots of validation tasks on that same model. So with out-of-band validation, they were enabled to perform even more validation and test steps that they could do before.
Like the type models, I'm more interested in that. And the Gen AI models are like models to create embeddings and like that sort of.
Yeah, I think this one was on fine-tuning of an image generation model. Yeah.
What's the range of data set sizes you deal with?
Do you want to answer this one?
The range of dataset sizes, there's quite a huge range because like Amar said, we have various teams that range from search, recommendation, and image gen. For the image gen one, the recent annotation that we did, that's the fund.
700 million?
700 million images for one of our recent annotation tasks. Yeah. Probably will get bigger. Yep.
So you use a monorepo. So your users might have contention over dependencies.
So this is about the monorepo dependencies. Oh yes, all the time. It is a a pain to have to upgrade Torch because you are then responsible to make sure all the other Torch models in the repo don't break. But then it's also up to the corresponding teams that own the models to have sufficient unit tests that test this, because ultimately if CI passes, then you can merge it. Yeah. So it's a shared responsibility. Yeah. Same setup for inference. Yes, it's all in the one mono repo. So the checkpoints? So the checkpoints are just sent to S3, and then the final artifact is in weights and biases registry, and then at deployment time, it gets it from weights and biases registry and layers it onto a container. That's it. Thank you.